Hello everyone, welcome to the next lecture on bipolar junction transistors. So let me give you a very quick brief summary of what we talked in our last lecture, or the first lecture of BJTs. We started with the introduction to bipolar junction transistors. We saw this physical structure. This is a three-terminal device: emitter, base, collector are the three terminals. So there are three semiconductor regions for this device. So N-type, P-type, N-type. So that is why it is called as an NPN BJT. Two junctions, emitter-based junction and a collector-based junction here. Similarly, we have a PNP transistor where emitter, base, and collector. Emitter is P-type, base is N-type, collector is again P-type, considering the naming conventions. So we saw that physical structure. We talked about very briefly its modes of operation. If we cut off, reverse bias both the junctions, the no current will flow and the transistor will be in the cutoff mode. We can also operate the transistor in the active mode when our emitter based junction is forward biased and reverse collector based junction is reverse biased. We can also operate the transistor in the saturation mode when both the junctions will be forward biased. Today we are going to talk more about the active mode and the equivalent circuits. Okay, so specifically for the active mode, we saw that how the current will flow in the active mode. This is for the NPN transistor being operated in the active mode, which means that our emitter based junction was forward biased, collector based junction is reverse biased, right? So this is our emitter based junction is forward biased, where our P type is at a higher potential as compared to the N type, and our collector based junction is reverse biased over here, where our collector, which is N type, is at a higher potential as compared to the P types, so our collector based junction is reverse biased. So we saw that how the current will flow. When we forward bias the emitter based junction, we have a lot of these free electrons over here that will be injected from the emitter to the base region. Some of these electrons will be combined with the free holes of the p-type material of the base and lost in the recombination process. But since the emitter is very heavily doped as compared to the base, so though that loss of these injected electrons will be very minimal, and most of these electrons that were injected over here in the p-type material or in the base will be swept across the collector to base junction into the collector terminal, and constitute the main collector current, right? So our collector will be positive here. So that is why we have just a very minimal loss of the electrons in the recombination process over here. However, rest of the electrons were swept across to the collector, into the collector terminal. So these electrons constitute mainly the collector current. If we look at the emitter current, our emitter current has two components. One of these components is these injected electrons from the emitter to the base, and the second component is this holes which were injected from the base to the emitter region. Similarly, our base current is also composed of two components. One is the same component as this, as emitter current, which is the injected holes from the base to the emitter, and the second component has to do with the externally drawn holes from the external circuit, equal in number to the holes that were lost due to the recombination process in the base terminal, or in the base region over here, equivalent to IB2. So that is why these are the direction of the current flow. We have an IB direction over here, IE and IC over here. We also saw that IC equals to IB plus IC. Our emitter current is equal to the base current plus collector current. And by looking over here, IC, we know that IC mainly so the current that constitutes the IC is mainly controlled by these electrons that were starting from the emitter terminal, right? And that amount can be controlled by the biasing voltage over here, VBE. So we found the equation for the collector current, which is equals to the scaling current and the exponential relationship with the biasing voltage, VBE. Similarly, we saw that the base current was just a fraction of the collector current, which can be related by this beta factor. So our beta was equals to IC over IB. So we saw that this beta can also be referred to as a common emitter current gain. We are going to talk more about this thing today. Similarly, we found out the emitter current, which was the summation of the collector and the base current. And emitter current can be represented by alpha times, collector current can also be referred to as alpha times IE. So if I will write alpha, it is IC over IE. So alpha was known as a common base now, common base current gain. We are going to discuss both of these alpha and beta current gains in more detail today when we will make this equivalent circuit models. Okay, so with that, let's start our today's lecture. In today's lecture, we will develop large signal model equivalent circuits, and we will see this common base model and a common emitter model, and we are gonna discuss more about this alpha and beta. Okay, so this is in terms of, so before developing equivalent circuit model, this is what we know so far. When we operate an NPN transistor in the active mode, we forward bias the emitter to base junction. So this product biasing voltage will exponentially increase the current IC, right? Because our current IC is proportional to IS VBE over VT. So we can see from here is that our collector current can be controlled by the biasing voltage. So we will realize that we can operate this as a constant current voltage control source. Another important thing that we realized by now is, since our collector to base junction is reverse biased, right? Since it is reverse biased, so this means that our collector current is completely independent of the biasing voltage that we applied at this junction, right? And the collector to base junction can be reverse biased when this voltage value is greater than 0. Again, assuming the PN junction to be an ideal model. Very shortly we're going to talk about as a real model and how to overcome the barrier voltage and what are the exactly threshold values. For now, considering the ideal model, once our collector to base junction voltage is greater than or equal to 0, this means that the collector to base junction is reverse biased and our collector current is completely independent of the collector to base junction biasing voltage value, and will depend only on the emitter to base junction biasing voltage. Okay, so in this active mode of operation, just by looking at this equation, we can realize is that we can operate this transistor, or the current that is flowing in the collector terminal IC over here can be controlled by VBE, or the biasing voltage. So we can operate this as a constant current source controlled by the voltage VBE and IC over here, right? So we can operate this as a constant voltage control constant current source. We also saw that the base current is a factor of 1 over beta of the collector current, right? So our base current is collector current over beta. We also saw that emitter current is the sum of the collector and the base current. And since our beta values are usually very, very large, right, our base current values goes very small. As beta value increases, our base current values go small. So for example, if beta value is very, very larger, then our emitter current is almost equals to the collector current, because our emitter current is equals to the base current plus collector current. So if this value is very small, I see emitter current and the collector current are potentially almost very similar. Another important thing over here, so our emitter to base junction in the active mode will act as a diode, and we are going to delve more deeper into this phenomenon. Okay, so here are the equivalent circuit models. So let's discuss all of these models in detail. So we have an A, B, C, and D here. Okay, so let's look at the figure over here. In this figure, we have, again, this is a model of an NPN bipolar junction transistor. We have 3 terminals: collector terminal, base terminal, emitter terminal. Okay, great. These are the directions of the currents that we can see, and these are the directions of the current that are coming from here. If you want to go directly into the basics, right? So your base current goes into the base terminal, collector current goes into the collector terminal. So the electron's direction was this, right? So the collector current is in convention opposite to the flow of electrons, so it goes into the collector terminal, and emitter current flows out of the emitter current, which is a summation of the IB plus IC. Okay, now we can say that okay, so we this in this model we have three terminals: collector, base, and emitter, and we can see that now let's look at the branches. Our collector current branch, we earlier we just saw that it can be operated as a constant current source controlled by the voltage, right? So this is the equation of the collector current. So we have it can be controlled by, so this is a scaling current, again a transistor parameter, and then controlled by the biasing voltage VBE. So this is the biasing voltage that we apply across this junction, right? So we have this junction, base to emitter junction here, and we forward bias this junction by applying this biasing voltage VBE. So this biasing voltage will control the amount of the collector current that is going to flow by this amount, by this equation, IS VBE over VT. So that is why this is a constant current source controlled by the voltage, or a voltage controlled current source. So this is our IC, this is our biasing voltage. And we know that when our base to emitter junction, when forward bias, can be modeled as a diode. So we can model it as a DE. Over here, diode labeled as DE over here. Okay. So the current that will flow through this emitter branch will be equals to IE. Now, another important thing, if we look at this model slightly more closely, we can, excuse me, so we can see that this is something similar to a common base model, right? Where or something, it is behaving like a two-port network, where our base is common in between emitter and the collector. So this is one of the ports, and this is our second port. So this is something, a common base model. Okay, so now in a common base model, we saw that our collector current is proportional to alpha times IE, right? So we are interested in finding out what is the current IE that is flowing over here. So what we can do is IC equals alpha times IE, so we can replace this value over here. So alpha IE equals ISE VBE over VT. So IE equals to IS over alpha E VBE over VT. So this is the scaling current ISC of the diode, right? So this is ISC is the scaling current of this diode DE. Scaling current of this diode DE, of this diode. So that is why over here, the scaling current over here is written as IS over alpha. So our IE over here will be equals to ISE e raised to power VBE over VT, where ISC over here equals IS over alpha. All right, so this is how we can model this common base configuration over here and develop this equivalent circuit model. Another important thing that you realize in any of these PN junction, that this is always going to be an exponential, nonlinear exponential relationship in between the voltage and the current, right? Or even for the currents. For a collector current over here, even if you look at the emitter current equation or a collector current equation, right, they all follow this exponential relationship. Now, let's go over here. So what we did over here, we have the same common base model in this B as well. The only thing that we did is we have replaced this IC value over here by alpha times IE, right? So when we replace this IC by alpha times IE over here, we can realize that we can also see this as a constant current source again. But what is it being controlled with? It is being controlled with current as well. Now it is being controlled with IE. Now our collector terminal and or the transistor is being modeled. Our collector terminal is being modeled as a constant current controlled by the current as well. So it's a current controlled current source. Okay, so these two models are very similar. We just ended up replacing this voltage value over here with the alpha times IE. Now let's look at another model in which it's a common emitter model. Okay, so these two models, C and D, are common emitter models over here, equivalent models. So what is the difference, or how we ended up reaching to this model? So very quickly, the only thing that we did over here is right? So this is our base that is going in. So our base is going in, our base current is going in, our collector current is coming out over here, emitter current is coming out over here, collector current is going in over here. The only thing that we ended up doing is we ended up shifting this, let's say this collector over here, right? So you can, for example, shift this thing like this, right? So one is this. The second thing is we, rather than ended up making a common base, we ended up making a common emitter. Now you can see that we still have a base current that is coming over here. We have a collector current that is coming over here, and they are all coming to this node. So our this model, we can easily see that it's a common emitter model, right? It's still a two-port network where emitter being the common terminal in between base and the collector, right? So our one port is base emitter port, and the other port is a collector emitter port. Now let's look at slightly more in detail over here. Again, our our collector current over here is a constant, is a current source, right? So this is a current source which is controlled by the voltage. So it's a voltage controlled current source. However, let's look at the branch at the base terminal. Right now, our branch at the base terminal, rather than representing it as a DE, which we did over here, it is being represented as a DB. So what is the difference in between DB and DE? So DE represents the diode for a common base model, which is appearing at the emitter branch, and now we have a DB diode, which is appearing in this base branch, and is representing again the PN junction of the base to emitter emitter base junction diode. There will be a slightly difference when we model it as a common emitter configuration. There's a slightly difference in the scaling current that we will obtain. In this configuration, we know that for the common emitter configuration, our base current was equals to IC over beta, and our beta is equals to IC over IB, right? So we find out, earlier we discussed that this equation is a current gain, right, for a common emitter. So this is our common emitter model, and so if we will replace this factor now, IC equals beta times IB, if I will replace this over here, what I will get is, so beta times IB equals IS EVBE over VT, so IB equals IS over beta EVBE over VT. So this is the base current that is flowing. So what we were interested in finding out this base current that is going to flow over here, IB. So the scaling current from this diode, which is due to the base current, is IS over beta rather than IS over alpha, right? Because this scaling current that is that is the saturation current of this IB equation. IB equals to IS over beta EVBE over VT is mainly constituted by the scaling current IS over beta. Okay. So what we did in the D model now, essentially everything is the same. Rather than using this equation, we ended up using beta times IB, right, from the over here. And if we will replace it over here, this will become a constant. This will become a constant current source controlled by the current, right? So it will become a current controlled current source. Again, these are considered to be the large signal equivalent circuit models. And again, the process is very simple. The first two models are the common base models. This A and B are the. Let me pick this. Okay, so this A and B are the common base models, and C and D are the common emitter models. The only difference over here, our collector current equations are the same, IS EVBE over VT. The only difference is when you consider it to a common base, we were interested in finding the value of IE, emitter current, and our emitter current for a common base model can be written as IC equals alpha times IE. And similarly, for a common emitter model, our base current, we were interested in finding the value of the base current, and our base current is equal to IC over beta. So now if we look closely over here, right, so this is our alpha equals to IC over IE, and beta equals to IC over IB. So that is why we called earlier alpha as a common base current gain, and over here our beta is a common emitter current gain. So these are the terms that we introduced earlier, and I hope these are more clear now. Okay, so this is all the explanation that I just said or talked about in these models, right? So this in this model B over here, right? So this is the common base model. Our base is, it's a two-port network. Base is a common in between collector and the emitter. And we ended up obtaining this alpha, which is a common base gain, common base current gain. Similarly, we talked about in model C and D that rather than having a diode DE now, we have a diode DB here, right? And this diode DB, the current that will flow through this diode is constituted by this base current IB. Right, so the scaling current that it will depend on is equals to IS over alpha, IS over beta, and we ended up finding it out over here. Sorry, actually over here. Okay, similarly, we saw that this model again is a model for the common emitter, and our beta is a common emitter current gain. And finally, these are the large signal models. We're also going to talk about the small signal models in the few lectures in the future. Okay, so we ended up developing these equivalent circuit models. Let's do one example on how we can potentially use it. Okay, so let's go to this example. Okay, so consider this example. Now we have an NPN transistor. The scaling or the saturation current is this. Beta value is this. Again, beta is a common emitter current gain. Plus the question already says that the emitter is grounded, right? So it should be a common emitter. Further, the base is fed with a constant current source supplying a DC current of 10 microamperes. So this is the base current. So base is fed with the 10 microamperes current. Further, the collector terminal is connected to a 5-volt DC power supply via a resistance of 3 kilo ohms. Right? So at a collector terminal, we have a resistance of 3 kilo ohms that is connected to the supply, 5-volt supply. So the first thing that we need to do is we need to, let's assume that the transistor is operating in the active region. We need to find the base to emitter voltage value and collector to emitter voltage values. And then we need to verify the active mode of operation. And then we will come back to the later part of this question. Okay. So since we know that the emitter is grounded, so if I have to draw an equivalent circuit model from the models that we discussed, so which of the models I'm going to use? I'm going to use one of these models, right? Either I can use a B, C model or a D model. They are one and the same. Okay, right? So we can use one of the 4 possible equivalent circuit models. Since emitter is grounded, we can use either model or C. Since we have a base current given, we can use, we can use a D model. We can potentially use a C model as well. And potentially replace this IS value, this collector current value by beta times IB. Okay, so anyways, here is the model that we have. Again, this is the model that was coming from that earlier that we discussed, right? So we have a base terminal, collector terminal, emitter terminal, right? We have a base current that is flowing, emitter current that is flowing, and a collector current that is flowing. So this was a model over here, C or D. So what we ended up doing is we ended up putting these extra values here that were given in question. The base was fed by 10 micron amperes, right? So our base current over here will be 10 micron amperes. Then we have a collector terminal is connected to a resistor, 3 kilo ohms. That was provided over here, right? So collector is connected to a 5-volt DC supply and a resistance. So we ended up putting a resistance connected to a 5-volt supply. And what we are interested in finding out the value of the base to emitter and the collector to emitter, right? Since our emitter is a common, so we need to find out this value, VBE, and we need to find out the value in between collector and the emitter terminals. Okay, so we know that let's start with finding out this value, VBE. So we can start with VBE. So in order to find out the VBE value or the potential drop across the diode, we know that it will follow this exponential characteristics. And if you remember, the diode stepper, we can write this exponential characteristic something like this, right? So we have a thermal voltage and the natural log of this ratio of the currents, which is the current flowing through the diode to the scaling or saturation current over there. So let's see if we have to rewrite this equation more precisely for our circuit. Our V is VBE over here. This is a thermal voltage, 25 millivolts. Natural log. Current I is IB over here, base current. And our scaling current, right? So it should be ISB, right? Okay, and we know that this ISB, if I will go back over here showing you, right? So our ISB equals to IS over beta, right? So we can call this as IS over beta, right? So you can write this equation over here. Now let's see if we have all of these values. Our VT is 25 millivolts. Base current, we know that 10 micron amperes. IS is given over here 10 to minus 15, 10 to minus 15, and beta value is 100. So we know all the values. Once we put in all the values over here, we can, the answer that we will found is 0.69 volts. So the value, our base to emitter voltage that will appear will be equals to 0.69 volts. Okay, so great. Now let's find the voltage, VCE voltage, collector to emitter voltage. So how we can find the collector to emitter voltage? Actually, that's even more easier, right? A simple Kirchhoff's voltage law, right? So our VCE equals to VCC minus ICRC. We know the value of RC, 3 kilo ohms. We know the value of VCC, 5 volts. We don't know the value of IC. Okay, so let's find the value of collector current first. Right, okay, so we know that our collector current is equals to, right, so we know that IB equals to IC over beta. So collector current is beta times IB, right? So collector current is beta times IB. Beta is 100. So we have 100 into the base current. Base current is 10 micron amperes. Where's the base current? Yeah, okay, 10 micron amperes or over here. Okay, so 10 micron amperes, we can find out this value. So 10 to the 3 into 10 to the minus 6, 10 to the minus 3, so it should be 1 milliampere. So we can put down this value over here now to find out the value of VCE. Okay, so this is what we just did. Okay, so this is IC value. Okay, so our value of the VCE that comes out to be is plus 2 volts. Now what we are interested in is to find out whether we needed to verify that we actually have a active mode operation, right? In order to have an active mode operation, we wanted to see that if our emitter to base junction is forward bias and if our collector to base junction is reverse bias. Right, okay. Okay. All right, so what is our values? We have a VCE, which is 2 volts, and our collector voltage is 2 volts, and we have a VBE 0.69 volts. So our base is 0.69 volts since emitter is grounded, right? So our VE is 0 volts. So just by looking at all of these voltage values, if I have to find out, right, the value of the emitter to base junction, right? What is the value of the emitter to base junction, or VBE? Then what is the value of VC? This is 0.69, right? So this is positive. So this means that emitter to base junction is forward biased. Now let's find out whether the collector to base junction is reverse biased or not, which is VCB, right? So VC is 2 volts minus 0.69 volts, right? So this will come out to be 1 point something volts, right? Since our collector voltage is much larger than the base voltage, right, or our collector terminal is at a higher potential for a base rather than a base terminal in an NPN transistor, so this means that our collector to base junction is also reverse biased. So this verified our active mode of operation. Okay, so let's do the second part now. In the second part over here, what we need to do is we need to replace the current source with a resistance from the base to the 5 voltage supply, and what resistance value is needed to have the same conditions. So what that question is asking is, all you need to do is to replace this current source, change this current source, take it away, and connect this terminal to a 5 volt supply. Take out this current source and connect a resistor over here. Instead have a resistor and find the value of this resistor such that you are going to have the same conditions. Having the same conditions means that you're going to get that same base to emitter voltage value, you're going to get the same current IB. Okay, so this means that this is what I need to do, right? So all I ended up doing is I took out the current source here and connected a resistor here, and I needed to find the value of the resistor such that it is going to have the same value, okay, such that it is going to have the same value of the IB. IB was 10 micron amperes. Okay, right? So this can be very easily done again by a Kirchhoff's law. So our RB is equals to VCC minus VBE over IB, right? What I wanted to make sure that I wanted to find the value of this RB such that the base current will remain the same and the base to emitter voltage remain the same. So the best way to do is just to put down the same values, right? So it will be 5 volts minus VBE 0.69 volts over base current 10 micron amperes. This will give the value of the RB, which will come out to be 431 kilo ohms. So this is how you can solve this problem. Okay, so this is good. Let's do one more quick topic and before we wrap up our lecture today. So let's look at the structure of the actual transistor. So here is a actual cross-sectional view of an NPN transistor, NPN BJT. Emitter terminal, base terminal, collector terminal. These portions are the metal contact pads to these extrinsic semiconductor regions, right? So we have an NPN region. So the things to notice over here is that this structure is not symmetrical. So if we have to, in terms of biasing the transistor, if we have to interchange the collector and the emitter terminals, we cannot and we should not. And this is in contrast to a MOS-FET, where our structure was very symmetrical in nature. And we can, even if we want, we can change the two terminals. So we have a gate terminal, source, and the drain. Yeah. So we can easily interchange the source and the drain terminals if needed because the structure was symmetrical. However, in the BJT, our structure is asymmetrical, so collector and the emitter terminals cannot be changed. Some other important things that we can see it over here. Our emitter to base junction is much smaller as our collector to base junction area, right? So our collector to base junction area, right? So if I will look at these terminals and the areas over here, so our collector to base junction area, is this area is very bigger as compared to emitter to base junction area. So important. So what is the consequence of this area? The consequence of this area is that I know that the saturation currents of these junctions is proportional to the cross-sectional area. So this means that for the collector to base junction saturation current for this junction is going to be much larger as compared to for the emitter to base junction, right? So this collector to base junction CB is going to have, for example, we can label it as a diode C. So the saturation current for the diode C, ISC, is going to be much larger as compared to for the diode E. Right, so ISC is much larger than a saturation current for the diode E. Right, this is diode C, this is diode E, because the area for the collector to base junction is much larger as compared to the area of the emitter to base junction. And for example, this scaling current, saturation current is approximately 10 to 100 times larger than the scaling current for the for this diode DE. Okay, so with that, we are going to finish our lecture today. Again, in our lecture, we developed equivalent circuit models for the large signal models for active region of operation of the transistor. We discuss in more details the common base models and the common emitter models. And importantly, in the common base model, we discuss that alpha is the common base current gain and beta is the common emitter current gain. We also saw that how we can use these equivalent circuit models to solve this example. We did this example. and discuss very briefly the structure of this how the structure of the actual transistors looks like. So in the next lecture, we are going to talk about, by now we have talked very in detail how to operate the transistor in the active mode. Now in the next lecture, we're going to talk about how to operate the transistor in the saturation mode. Okay, so with that, thank you so much, and I will talk to you in the next lecture. Bye bye.